offshore wind build out in the North Sea and the Baltic Sea. So it's interesting to hear also your perspective. We continue on the sea, I can see. Nina Dupont is a consultant with an analytical background and good knowledge on the energy market. She has focused on the integration of renewables in the energy system, analyzing the benefits of different types of integration measures. She has worked with several mathematical tools and energy models to perform simulations and analysis of energy systems. In particular, Nina has extensive experience applying the Balmoral model for power system analysis, including projects aimed at building, using, and transferring the model for applications in Europe, Mexico, and Vietnam. So, Nina, the floor is yours, or the screen is yours.
Thank you, Anka. Can you all see my presentation?
Yes.
I will try to put it in presentation mode.
Yes.
Yes, so thank you very much for having me. I will talk today about two projects we have done with a big focus on offshore wind build-out. The first project I will talk about a little has the focus on the Baltic Sea region. And in the second project that we did for Ørsted, we looked in general at both the North Sea and the Baltic Sea, Europe in general, and the impact of offshore wind build-out on the transmission infrastructure. I think many people that are here have been introduced to this. Oh, something changed. Can you still see my screen?
Yes, we can see the second.
It was just on my end then.
Okay.
Many people who are here today have been introduced to the Balmoral power system modeling tool, but just for those who are not familiar, this is the model that we've used for both the projects that I will discuss later on. Balmoral is a least cost optimization tool, and it finds the least cost solution when looking both at the dispatch side, so the generation of the individual generators and the flows on the transmission lines, as well as at the same time optimizing investments. Again, both generation and transmission. So it's very much a bottom-up model. It's also open source. I think there's versions of it that can be found online. And it's in general, it's a very transparent model. All the formulas and equations are visible for those who read the GAMS language. It was also developed actually by in DTU by Hans Raun. So I guess many of you are already familiar. Yes. So the first project I'd like to talk about is a study on the Baltic offshore wind energy, which was a study we did under the BEMIP work group. BEMIP stands for Baltic Energy Market Interconnection Plan, and it's a working group under the European Commission. It's a little bit of an older project. We finished it in June 2019. And it was a cooperation with the THEMA Consulting Group, which is a Norwegian consultancy who had the main lead of the project. And we also worked together with COWI, who had the task of mapping out the physical technical potential for offshore wind in the Baltic Sea, where then us, AI Energy Analyses, we did the market analysis and the kind of system integration aspects. So just a little bit about the study objective and the overall setup. So we looked at this Baltic Sea region. We wanted to assess the wind potential in that region, both what is the physical potential, so the kind of how much wind can fit in that sea, but also looking at the economical aspects. And by doing that, we also wanted to look at the opportunities and the obstacles for a coordinated development across the Baltic Sea region. So what is the opportunity for not just having national targets, but having a more coordinated development. And we did that by looking at 6 scenarios, which varied over 2 dimensions. We had the level of ambition, low level or ambitious scenarios, and I'll get back to that in a little bit. And then we also looked at 3 levels of how, what was the level of interregional cooperation. So the lowest level on that dimension was the national policies. So each of the countries that are in dark green on the background, they had their own policy for offshore wind, and they had to fulfill them within their own kind of sea domain. And then in the next level, we had the same kind of policies, but we also allowed, we also implemented hubs. So that meant that there were specific by us chosen hubs implemented, in which the offshore wind could then be used to be transported or to 2 different countries, or the hubs could also just be used to transmit electricity from one country to another. So there was this extra benefit and this extra kind of grid cooperation level to the scenarios. And then the last scenario level was where we had the ambitious overall goals, where so the same amount of offshore wind was kind of enforced into the model, but the model could choose where across the countries to place that that capacity. So the first kind of step in the overall project was that COWI kind of defined the physical technical potential in the Baltic Sea, and they did that by doing a GIS-based analysis, looking at the whole sea region and taking into account the distance to shore, the depth, the sea depth, natural reserves, and shipping lines, and other uses of that sea region in general. And they came up with around 200 sites and a potential of 100 gigawatts in total. And then 2 scenarios were developed on that low versus ambitious offshore development dimension, which can be seen here to the right. And the first, the low offshore development scenario kind of slowly increased until 2030. I think this is around 6 gigawatt. And then in 2050, there is around 17 enforced into the model offshore wind capacity in the Baltic Sea. And then the ambitious development is more or less double that amount. But both scenarios are still well below the total technical potential that was here defined by COWI. So we put those sites that COWI found into the Balmoral model, and we took into account, so we differentiated the costs based on the parameters also COWI indicated, which meant the distance to shore was accounted for, and also the foundation cost depending on the seabed level. And then of course the wind resource was also individual for each of the sites that COWI found. And then here on the left, for the low national policy scenario, we have the LCOEs for each of the Balmoral regions in the model. And there's a clear picture here that the LCOEs are actually quite high here in the north, close to Sweden, and then are lower further south. And that's mostly due to the, I should also say this is in 2030. So that's mostly due to the wind resource quality. So in the further south, there was a bit higher wind speeds on average than here for north. And I should also say that this is the LCOEs of the capacities that were actually forced into the model. So of course, if for the more ambitious scenario, these LCOEs would increase in general, because you would force in more capacity, and therefore you would also force the model to invest in offshore wind that is more expensive and further out. And here on the right side, we have the offshore market value, again in 2030 for the same scenario. And here we see kind of the opposite picture. So I just should say that this is not the average electricity price. This is the price that offshore wind sees. So the market value for offshore wind. And here we see kind of very like higher values in the south, and then quite a lot lower values here up north. And the reason here is that here in the north, around North Sweden and Finland, the model found alternative RE resources actually more cost efficient, namely onshore. So the market value here for offshore is quite low compared to the value we found further south. Then if you subtract one from the other, this gave us kind of an indication of the value, or you could say the cost per megawatt hour of the different offshore wind regions. And one conclusion we could draw from that it is definitely possible to have grid parity for offshore wind already in 2030 in that low national policy scenario. And that would be indicated by these negative values here, which means a negative cost versus value for offshore wind. And that, of course, all this indication where there's such a wide spread over this cost / value indicator also shows that there is quite a big potential of optimizing if you want to have a large build out in the Baltic Sea region, that there's a value in optimizing where to place it rather than each country sticking to their own policies. And yes. So that the previous few slides were very focused on the offshore wind evaluation, where we also looked at the total system costs, because in each of the scenarios, we didn't only force in offshore wind, we also allowed the model to optimize the remaining power system, so onshore. And then we looked for the different scenarios. We compared the total system costs, which included the CAPEX costs for both for offshore, but also for the other generation, OPEX costs, fuel cost, and greenhouse gas emissions cost. In this case, that was just the CO2 price that we put on, and we made a projection of the ETS prices. And here we see the differences in total system cost between the ambitious and the low scenario, both for national policies. And you can see here this gray part is the additional cost that is due to the additional offshore wind that we foresee in the ambitious scenario versus the low scenario, which of course is an extra cost, but then all the other costs are actually reduced as a result of that. The blue part is the other CAPEX for the other generation, and then we have OPEX in green here, fuel costs and CO2 costs. And we see that even though there is quite some reduction in other costs in 2030, in the national policy scenario, going from the low to the ambitious scenario is actually not beneficial at that time yet. Because we see an increase of additional cost. But in 2050, we have this small reduction indicating that actually there is a positive value to having more offshore wind enforced in the Baltic Sea. Even if we saw that, even if we are now talking here about the national policy scenario, and we saw that it was beneficial not to have your own policies, we see that still there is a benefit of having larger amounts of offshore wind in the system. Then we also compared the differences between grid cooperation and the national policy. So that would be these two scenarios. And that would the grid cooperation scenario is the scenario where we forced in those hubs And we see here that in 2030, this is the cost of the hubs, and we also see an increase in offshore wind turbine cost, and that is because the hubs were chosen in a kind of in locations where it's possible to make hub connections or more advanced connections, and those are a bit further out at sea and with a bit lower seabed depth. So there is also an additional cost, even though the total capacities are the same. There's an additional cost to moving offshore winds further out at sea. So in 2030, this showed that actually there is there's no benefit, and there is actually a cost associated with implementing those hubs. We also looked a bit more in detail at those different hubs that we implemented, and it was also shown that some hubs are actually beneficial while some others were not. So it's also a bit arbitrary. Which one, if we had chosen maybe only one of them, there could have been a value to adding the hubs. However, in 2050, there's a clear indicator that adding those hubs to the system actually gives a benefit to the overall costs of the system, and we have a reduction in all other costs. Yes, and the reason here is by 2050 already we had quite a higher target, and so in any case more of the offshore wind was forced to use more difficult sites, you can say. So adding the hub only gave the benefit of having more connection between countries and having the choice of where to transmit the power from offshore wind to. And then in this last slide about this project, I will show a bit the last step that we had in that project, which is that we used the Balmoral optimized capacities, and we actually implemented that in the more detailed grid model from TEMA. And this was just to show that there is a big impact of the offshore wind build out also on the transmission grid. So here we see the low scenario, and here on these lines, it's kind of showing how often the transmission lines are congested or how much they're used. And these are mostly green lines. This is Poland. And then if we go to a more ambitious scenario, we see that more and more of those lines are actually heavily used compared to the base case. And then if we use those ambitious scenarios with the hubs, that this results is even seen even further because one of the hubs connected Poland to Sweden, and the extra infeed from offshore wind from that hub also impacted, from that Swedish hub also impacted the infeed and the onshore use of those transmission lines. Yes, then that was the Baltic Sea region study that we did. And then last year, this was, I think, finalized, I think also in the summer of 2020. We had a project on offshore wind and infrastructure in Europe for Ørsted. And just as a bit of background for this analysis, we used the European Commission's 2050 long-term strategy as a baseline for the setup of the scenario, and we used the 1.5 tech scenario to do this. And one important, clearly obvious thing that was part of this 1.5 tech scenario is that there's a very large amount of power to X in the system expected in that development. It's also a net zero scenario in the power sector. So it's quite an ambitious scenario all in all. Yes. And I would just show a little bit more about how we implemented this power to X in the Balmoral model. So we implemented it as a demand for that combined fuel that we called power to X. the 1.5 tech scenario just gives a number for the entire Europe, and we have divided that number across the regions in the Balmoral model based on their current energy demand for transport and industry. So some countries will have a higher share of their power demand related to the power to X need. And then in the model we allowed, so the demand is distributed over the regions, but in the model we allowed the production of that power to X to be relocated or located wherever it was most suitable. And then once the power to X fuel was produced, it can be transported to the region where the demand is at a cost of 30 euros per megawatt hour, which from sources or from opinions of experts we heard was quite conservative estimate, so that this is quite a high cost to assume. And this cost should also be said that it's kind of a rough representation, because this cost was the same whether you wanted to transport power to X from Norway to Italy or from Netherlands to Belgium. So it was just kind of to give an indication. Yeah. And then, of course, for offshore wind resource, we kind of did a step beyond what we did for the project I just explained previous, is that we, instead of only differentiating the costs for the different sites, we also actually chose some specific sites and modeled them as specific regions, meaning that the costs are not, for transmission is modeled explicitly, where in the previous project the cost of transmission from shore to the site was modeled as part of the wind farm cost. In this representation, it was actually modeled as a transmission cost between regions, which also meant that we had the option to allow for meshed interconnection between the different sites that we are modeling. Yeah. We had a main scenario, which was a radial scenario that I'll briefly discuss, and then we had a range of sensitivity scenarios. And today I will only discuss the first two sensitivities. One was kind of a meshed multi-linked hubs scenario, which was kind of placed directly against the main scenario, where it was only radial connection, and now we have a meshed scenario. And then we had another sensitivity where we didn't allow the model to redistribute the power to X generation. So wherever the demand for power to X was, that's also the place where it should be generated or produced. Just very quickly about the main scenario and the overall look. As you can see here, the main scenario is a very green scenario with a lot of solar and onshore wind, and around 350 gigawatt of offshore wind. And this was quite important to us, this number, because we wanted to at least reach the same ballpark as the 1.5 tech scenario. And the 1.5 tech scenario had 450 gigawatts, but represented a larger modeled area than Balmoral. So if we scale that to the modeled region in Balmoral, it was around 385, and we found that 350 gigawatt is quite close to that value. So this was just a quick check to see that with the input from 1.5 tech scenario, we were also quite close to their results, also in terms of emissions. And these last ones were emissions that the model couldn't reduce. Yes. So then some of the other results is about offshore wind build-outs, and where in which seas that does the model choose to invest the build-outs. And we can see that the majority of the offshore wind capacity, around 57%, will be found in the North Sea. These green blocks, they represent offshore wind capacity that is built in aggregated areas, and then these blue ones are the ones that I showed you earlier in those individual projects that we model with explicit transmission connection options. So quite a lot of that is also in those kind of projects. And the Baltic Sea in general had 42 gigawatts, so it's a bit less popular for investment, but it's also based on the optimization, it's also very much used. And then, of course, one of the key interests in this project was what is the impact on transmission lines. And we can see that in the main scenario where we only allow radial connections, we see a five-fold increase between 2020 and 2050 for overall transmission needs between the regions of the model. And the unit we use here is gigawatt times 1,000 kilometers. So it takes into account the length of the cables that are needed. And we see quite some increase in direct onshore connections. So that could be the connections between countries, France and Germany. But we also see the largest kind of increase is on offshore connections, not offshore wind, but direct offshore connections, like through the sea between, for example, Norway and Great Britain. And then this last part, these are the connections that we included to those individual sites of offshore wind sites, which of course also increase. So then the first comparison would be the radial one versus the multilink hub. And here we see that the total offshore wind capacity built out increases slightly, around 4%. But we see that the places where we allowed for this meshed representation, in those two, both in the Baltic Sea and in the North Sea, we see an increase of around 13-14% of offshore capacity, because that's actually where there is the value is to be had from allowing meshed interconnection. Sorry, wrong direction. And we also took a look at the transmission infrastructure needs, and we see that there's an overall decrease in transmission needs, and that's because more of the transmission can now be used both for getting offshore wind to shore, but also for getting generation from one region to another region. So this kind of was a more efficient way. The hubs, through the hubs, was a more efficient way to distribute the power from offshore wind. So we see this increase here in advanced connection capacity that is related to offshore wind sites, and then we have a decrease of 25% in the direct offshore connections, and a small decrease also in onshore connection. This is just as an illustration of how the model actually optimized those connections. And this is the radial situation, so the main scenario, where each of the capacities is simply connected to shore. And then on the right, this is how the multi-linked hubs looked when the model optimized it. And of course, the one takeaway from this figure is that this is not a realistic scenario, and that these very small lines would not ever be built in real world, but would probably be combined in some larger offshore corridors. But the simulations we did were more to illustrate and to get an indication of the value and the need for having this meshed multi-linked setups. Yeah, and this is the same for the Baltic Sea. And this also just to show that the big drop in transmission, in their indirect offshore transmission, can be clearly seen if we compare the two larger maps. So here we have, especially to Great Britain, we have these very large capacities here in the main scenario, which then are reduced because they're replaced by meshed offshore grid connections in the multi-linked hubs scenario. And then the second sensitivity was around this power to X redistribution and versus non-redistribution. And we kind of assume that that's also quite relevant, because if you're allowed to have the additional electricity demand, which, as you saw from the input slide, was a quite large share of the overall electricity demand, if that demand can be allocated to the places, for example, where a lot of offshore wind can be built, we had a guess that would kind of impact the level of offshore wind that would be built, and also the value of it. So here we can compare the power, the percentage of electricity generation, electricity demand out of the total demand in the, let me say that again, the percentage of electricity power consumption for power to X as a percentage of the total electricity consumption in each region. In the scenario where it's not allowed, the production is not allowed to redistribute, and here is in the main scenario where it was allowed to redistribute. And we see that in most regions, actually, there is a small decrease in how much they produce if they're allowed to redistribute the demand or the production, and that it's mostly Denmark and Finland in which we see a quite large increase of how much they produce for other countries. And for Denmark, the clear reason was that there is quite good offshore wind potential, and therefore with offshore wind, the very cheap electricity prices that are related to that made that generation of power to X was advantageous at that location. For Finland, the reason was more onshore wind. Yes. And then if we look at some of the indicators of that switch, we see that there's a lot of savings to be had by enabling this power to X demand distribution. So by playing out that synergy between offshore wind and for Finland also onshore wind and power to X generation, a lot of money can be saved in terms of system costs. And again, we also see a decrease in the need for transmission infrastructure. And in this case, in 2050, it's 15% decrease due to the ability to just move the power to X demand instead of moving the power around. Yes, I think that was all from me. I just have the links here from the two studies we did in case you are interested in more background information. And then I'm ready for questions if there are any.
Thank you, Nina, for your interesting presentation. Are there any questions from the audience? Meanwhile, maybe I could say that it is nice to see another type of study from another angle on this Baltic offshore. So compare with Tillman, came from another perspective. And it was also nice to see that by adding hubs to the system, that there are a lot of benefits, connections, and prices, as Tillman has also highlighted. Yeah, I was I saw that the optimization results give you a conclusion that the most offshore wind capacity will be in the North Sea in 2050. Can you so compare with the Baltic Sea? Can you elaborate a bit on the assumptions for this assumption, and which are the reasons you think that this is a result?
I think it's partly due to the higher resources. I think we found that the wind speeds, the average wind speeds, are a little bit higher in the North Sea, and I think there is also relatively low, or how should I say, high seabed depth. We have quite some. The differentiation of the investment costs is quite dependent on the sea depth. So I think that was also part of the reason that that the North Sea, that has quite shallow waters until further out, was more advantageous. I think there's also quite, when you look at the interconnection cost, there is a really big need of like in the scenario with the meshed grid, there's a very big need for, or the model is very keen to connect Great Britain to continental Europe and Denmark. So in that there is also that extra benefit of having offshore wind in those regions when you can interconnect them.
Thank you. Any questions? Kaushik, I saw that you raised your hand. Yeah, please.
Yeah, thanks, Nina, for accepting the invitation and having a very interesting presentation. I was wondering, did you have onshore also focus in it, or it was in like just out of the scope of your optimization?
Sorry, the onshore wind?
Onshore developments of wind, did you also consider in your investment, or?
Yes, yeah, we allowed full optimization of onshore and offshore and solar and of the whole system. The focus of the study was definitely on offshore wind. But yeah, so in any of the scenarios, the model was allowed to dynamically adjust the remaining power system based on the.
So what was limiting the onshore is because I would still believe in your model onshore is cheaper than offshore, but is it because of the only resources, or did you also take into consideration the social acceptance issues, or there were other issues as well which did limit onshore probably?
Yeah, it's a little bit of what we used for onshore wind is as a sort of limiting, and I think that includes some social acceptance considerations, is we have the technical potential, but we scale it all down to some development plan of Germany, and I think that ended up with 100 gigawatts of onshore wind in 2050. So we assume that as a realistic trajectory, and then we scale the technical potential of the other countries kind of downwards to that. So it's a bit of a mix of looking at the technical potential with the considerations of what is possible and what will probably be allowed. And I think for the UK we have an extra decrease of what for UK and maybe also Poland. I think we implemented an extra lower because we know they're quite avert to onshore wind build out. So we try to take a little bit the social acceptance into consideration. But you're right, like
yeah, I mean, we cannot do more than that, better than that.
Yeah.
I have another question before giving it to Damien. Maybe you did touch upon it, but I was thinking maybe you can go a bit more details on how did you consider the CO2 prices or CO2 taxes in your model, because that is probably required that at least in our model, what we have seen is required for decommissioning of the conventional ones, right? Otherwise, it will not push to the. Did you also have same feeling that if you did not put the CO2 price as high, you do not get?
Yeah, definitely. And we actually used the CO2 price from the 1.5 tick scenario, which was the 1.5 tick scenario. All of those scenarios from the long-term strategy is only for 2050. So we had that value for 2050, and then we used the forward prices here, I think, until maybe 2025 or something. And then we used the sustainable development pathway from the World Energy Outlook 18 for the intermediate 2040 step. So yeah, we this one we were quite firm on, and it's also very high. It's 350 euros per ton, so it's a powerful driver for having variable renewables in the system and reaching this very low CO2 emissions amount.
I hope this message is conveyed to the Commission.
Yeah.
all their strategies and vision, it doesn't go without the CO2 prices. But then I leave to Damien. Thank you.
Yes, please, Damien.
Hi, Nina. Thanks again for the presentation. Perhaps a clarification question or a comment rather than a question. I was just wondering about the revenue streams for the generators. Are you focusing on energy revenue streams, or are you also thinking about things such as flexibility and system service revenue streams, or even sort of capacity related revenue streams?
I think like the Balmoral model focuses, maybe I'm answering your question a bit too broad, but the Balmoral model optimizes socioeconomic costs. So it's not, the main focus is not really on the revenue streams of the individual generators. We don't, I think for some countries we include some capacity market implementation as well, but I think it's not very. It doesn't influence the results too much.
Okay, so what about those plants that, let's say, some of the conventional plant or some of the plant that isn't used that often? Is that encouraged within your model?
Those would kind of be taken out of the system if there was more. If the model is allowed to decommission them if they're not used at all. If they're used rarely, then they would stay in the system and would have very high power prices. So that's how the model kind of.
Okay, but I suppose what I'm getting at is that they might have very high power prices and they mightn't be used that often, but if there are extended periods when it's not windy or it's not sunny, you might find that you actually would like them to hang around. Yeah, and then of course on top of these results on Balmoral, policies would have to be developed to make sure that the costs are distributed in a way that it's feasible for everyone, including the generators. So there would be some kind of policy would be required to get to this setup. Okay. But that's not really that's not a direct result of the model. That's more a post consideration to be added on top of the. Okay.